Thank you for joining and coming to my talk. In this talk, we will be presenting the result of a collaboration between the University of Melbourne and MSc Software Hexagon. The talk is titled Flow Physics of COVID-19 Aerosols, and in this talk, we will be evaluating CFD methodologies or computational fluid dynamics methodologies, if that's a new word for you, and we're going to compare it to some experimental work. So why do we want to do this? And really, if you're coming laterally into this talk, what we're really doing is putting CFD to the test. And the reason we want to do this is that CFD is a widely used tool and it generates really nice results, but it is important that we take a step backwards and confirm that the results are accurate. So here is the result of some visualizations that Propel has made from MSc Software, and on the left you see a flow field that's been solved, and on the right you see some particles that are moving around this room. It's going to be referenced throughout this talk, but what we're really looking at is a simple room geometry with HVAC, which is present in virtually every room in the world. So a bit about me, the presenter. So my name is Tony. I am a PhD student at the University of Melbourne. I previously worked as a research and development engineer at Sealy International. I also worked as a research and development engineer at Veolia Wastewater. So if you want to get to know me better or collaborate with me or our group, the way to my heart is by going to strava.com. And my athlete number is 281-13988. So if you join me there, we can do further work together. So I'm based in Melbourne, Australia, and I'm part of the Andrew Uwe Research Group. And what we tend to focus on is high order, very accurate GPU simulations. So our day job is looking at turbulence, which I won't go down the rabbit hole of too much. But as you get as flows tend to go faster and faster, the scales of motion become finer and finer. And so in order to realistically capture these very detailed flow fields, you need high order and very accurate simulation techniques. But our expertise is versatile. We previously have worked with cardiologists where we were using imaging methods to reconstruct the coronary arteries on our heart, and we were determining whether or not we can predict the blood flow and so forth, predict whether this person would have cardiac arrest. So that's a bit about us. So today we're going to be focusing on these aerosol experiments where you see this simple geometry room laden with many, many particles, and those particles, just for reference, if you want to try this at home, are very small. They're 5 micron in diameter. They are dense, but I wouldn't focus too much on that. By virtue of their very small size, they essentially behave like fluid traces. So if you are somebody who wants to get into the physics of aerosols, something you should know is that in any room there are many background flows. They're not so easy to see, but they are there. And if particles are very small, they follow those small airflows in the room. But as they get larger, they sink to the floor. So these particles are very small and they tend to stay airborne for long periods of time. Again, if you want to try this at home, our room dimensions were 3.5 meters by 3 meters by 2.3 meters tall. We had a 55 meter cube per hour airflow from the HVAC, which corresponds to 2.3 air changes per hour, and the experiment went for 60 minutes. So I'm going to be presenting results from that first image I've shown you at the top, but we don't at the University of Melbourne only focus on that room. You can see this a study of a tutorial room where this research engineer, Grant Skidmore, is ladening the particles with ladening the room with many small particles. So just a little bit about our experimental facility. We have established laser sheet methods So what essentially happens is that this laser sheet shoots up and you have this smoke machine which is going to release many particles in this simple room, and we're going to have cameras here where my cursor is, and that camera will shoot through, and the amount of light intensity it sees from the laser sheet corresponds to how many particles are currently in that room. So we are a fluid mechanics research group, so this is really our bread and butter, to use these laser sheets to count particles, to measure flow velocities, to measure the speed of wind and that kind of stuff. So how did we get the idea for this study? Well, we were actually using this experimental room that you see, and we were actually using it to study the efficacy of air cleaners, so these portable air cleaners. And what we did was we got this fairly basic room with a HVAC and an airflow pattern, and we said if you got a smoke machine and filled this room with many particles, and you only had a HVAC, so no air cleaner for a moment, how long would it take for the HVAC to remove those particles from your system? So if you're a bystander standing in this room, you know, if you wanted to have half the number of particles in this room at what there was when we started the experiment, you'd need to wait approximately 20 minutes. And if you wanted a good shot of no particles in your inhalation, so if you want a 97% decrease or something like that, you'd probably need to wait an hour. And that's that curve there. But what we found was if you put in these air cleaners that suck in air and filter it, so they remove the particles from the system and just blow back fresh air, you could dramatically kind of decrease that time. So now we're talking 40 minutes or less, and as you put in more of those air cleaners, you're actually able to remove the particles more and more quickly. But taking a step back, so that was some work we did that was published for the medical community because they're interested in hospital rooms. But taking a step back, we removed the air cleaner, and we were just interested in using our laser sheet to see how many particles remained with time. So you see the University of Melbourne experimental data. We then simulated that room using MSc Cradle software, where we got what I will call a pretty good agreement. And to really put it to the test, we also included the data set from OpenFOAM, which I'll speak about in a moment. But if I'm commenting on these curves, you'll see that there is really good agreement between this academically oriented software and this versatile kind of MSc Cradle software that can tackle novel and real world and practical geometries, and OpenFOAM, so this software that is very accurate and really does its due diligence to make sure that those solutions are real. So I think that's a really good kind of hint that the accuracy of MSc Cradle is pretty good. There is a bit of a discrepancy here, and that's something that we will address in further experimental work and further modeling efforts, but it is in general quite hard to get really excellent agreement between experimental data and simulation. So just a few details. If you are somebody in the CFD community, we used a steady Reynolds average Navier-Stokes model. The particles were modeled in a Lagrangian frame, and we used OpenFOAM, finite volume method. So this is well accepted in the academic community with thousands of publications. It's one of the most rigorous and studied computational fluid dynamics software there is. And so the reason I'm saying that is we took our room here and we got a line on the center, and we got the velocity from both OpenFOAM and MSc software to compare it. And I'll comment again that as you move along this line, you get a shift in the velocity profiles where it is 0 at the wall, then it's quite fast some distance away, and then at the center of the room you have this quite high velocity magnitude again. So qualitatively, this agreement is really good. We're seeing the same trends in MSc software and in OpenFOAM, but it is really hard to get kind of perfect agreement within the RAND simulation community. So why might this be useful? Well, whilst most rooms contain things like desks, or they might contain chairs, or they may have people with buoyancy flows coming from their heat. So although the work we've done in validating the models is not going to be applied to shopping centres in the fourth, it does give us good confidence that those models work and that they are real and that the results that you present using commercial CFD packages can be trusted. So in the future, what we would like to look at is the understanding the flow mechanics of why putting in these portable air filters might make rooms safer, why they may, and which parts of the room may actually counterintuitively be less safe and need special attention. We want to look at designing real-world rooms such as lecture theatres, and we want to be able, using the CFD, to inspect, say, the corner of the room and understand what's happening in that region, and answering questions such as where is it safest and what are safe distances for students to sit apart if they're going to be attending a lecture. But the possibilities are quite wide in understanding, say, how many people can attend a shopping centre within an hour time frame. So that's the CFD side of things that we're looking forward to the future, but we have featured in the news our group. So this is Jason, who's the head of department at the University of Melbourne, and what they're interested in here is doing experimental work in a lecture theatre. So this is a lecture theatre in the engineering block, and you can see he's using this smoke machine to disperse the particles. So there's this jet coming out. After some time, those particles are dispersed all throughout the room with the assistance of fans. And then we want to answer questions such as how much of this flow actually leaks through gaps. So if you're a student studying in the next room to the lecture theatre and there is a sick person in the lecture theatre, how can we design the ventilation in that room such that if you are studying in the next room, it is safe? So here's a nice visualization of those laser sheet methods we use. So that concludes my talk. Thank you for listening. And yeah, feel free to get in touch if you would like to know more or if you have possibilities for what you'd like to study.